What are possible fixes? What do you think? So here, data block bitmap is allocated, but I know there's no information to locate these new data blocks. So this data block will leak. So we lost data block because I know those are not pointing, and also losing data block because file system keep data block is allocated in the data bitmap, but we can fix it. What are possible fixes for this case? So it scan inode and see that, oh, inode has no pointer for data bitmap. Okay, then in that case, drop it. Scan inode, all inode, and record that each inode having the blocks that pointed by inode. And then if inode says no blocks, scanning of inode result says no blocks in no blocks pointed no inode point to block number 5, then 1 2 0 1 2 3 4 5 block 5, then we know that this information is something wrong and fix the block bitmap. Okay, so this fixed information is done by file operation called FSGK. FSGK is file system checker. So it's a Unix tool which finding inconsistency in file system and repairing them. So when system abruptly crashes, so in normal crash, file system actually set the bit in the superblock. Oh, the file system is correctly, your computer system is correctly rebooted through the normal operation, then set a flag. But if this flag is not set, okay, so when first loading a superblock and then make this flag not set in the memory and persist the disk, and then in only normal legal rebooting or kind of shutdown process, then this superblock has set information. But in the crash, then this information has remained unset. So file system identify there's something wrong in the file system and then run FS checker. So FS checker, I just say it scans through all the metadata and data directory blocks and find the condition of contradictions, aka inconsistencies. Okay, so inode and data bitmap consistency or link count and duplicated inode pointer and other integrity checks. So I'll give some examples how FSGK works, fixing data block. So here's a case where inode and data blocks, but inode having a block pointer 5, but this block bitmap is not set. So how to fix in this case? Simply, how to fix it? Inode having a block pointer and data bitmap is not allocated. So set the bitmap simply. This information has guaranteed that inode update first, and then bitmap later. Because of this order, bitmap information is not applied after updating inode. So in FSGK, this case may possible, valid ordering case, and fix it. Okay, the other case, duplicate data block. So I see that your PDF file is a bit like there's animation is kind of overlap the blocks, so it may hard to understand. So I'm sorry for that, but this is actually kind of full slide So don't get confused with the the slide that actually kind of combined animations. Okay, anyway, so there are two inode pointing to same blocks. Okay, so how to fix it? In this case, how to fix it? Any idea? So file system know that, okay, yes. So because these two blocks are pointing to same one and data and know that, oh, maybe this inode and this inode, but we don't know where is new data. Maybe new data written here, we don't know. So kind of best way to solve this problem is copying data to new block, copy, and resolve inode 7 and allocate new with that. And resolve it. Okay, so that's the other operation of handling duplicate data block, case 2. Okay. 3, link count. So how do we pick which one to change? Oh no, there's no rule. So FSCK does not know which one is kind of pointing to copy the block. There's no rule. So simple way of applying this one is that inode number, larger inode number has the 1, 2 pointing to the copy the block. So there's not much kind of magic for it. How do we choose a copy destination? Learn the block allocator and then finding any free block. So there's no kind of rule for 7. So scan through it. Maybe 7 is fine, and the other block is fine. Just kind of grab the free any free blocks and allocate it. This is one example of copy. But so FSCK choose the 7. Okay, so that's the duplicate data block pointer. Second, in which situation data block pointers duplicated? Good. Here's case. This inode deleted. Inode 7, 1, 2, 0, 1, 2, 0, 1, 2, 3, 4, 5, 7. Okay, 7 delete block. And inode 2, inode 1 allocate block. Okay, and then persisted, but this one is not applied. So only inode 1 allocate new blocks updated. So this delete operation is not applied to file system because they are reordered, so they are pointing to same data blocks. Make sense? Because in case of in delete operation, file system says this 5 is not in memory struct says that data bmap says that flag is not used, so it's allocated to inode 1, and then when persisted, this block delete information is not written. Inode information not written, but this one first persisted. Therefore, there are 2 inode block pointing to same. Does it make sense? Will this check have some orders like checks data bmap first and duplicate it second? No. There are some kind of complicated things. For example, inode, if you look at the later inconsistency link, it also scans through directory blocks. But the most common approach is that allocating this scans through these inode blocks and then traversal all these namespaces, directory namespaces. So this is pretty specific implementation of FSCK. So yeah, that's actually kind of thing. Namespace scanning and inode scanning, moving back and forth. I know the very details, but when I look at the source code of FSCK, the rule for basic kind of implementation is first scan through this one, easiest one first, and then checking inode state and directory states first. Does it make sense? But don't look at FSCK code, super complicated. it just takes a week to completely understand FSK when I was a graduate student, but I just give up. Okay, yeah, okay, you did a good job. Okay, fine, but that's kind of a key thing. All right. So and second case is more complicated one. So duplicate inconsistent link count. If you look at the inode, there's a link count. So question: soft link, hard link. Who increase link count? Which operation increase? Okay, hard link. Okay, hard link increase link count. So some /AB/AC, for example, okay, pointing to same inode, and they inode link should be 2. So same scenario. So here's directory block, 2 directory blocks, and the foo file name foo pointing inode number 2. Okay, again, directory block says file name and inode number mapping. So scanning this one block and the other block, which finding a file name bar, which has inode number 2. What is it? These foo and bar are what? What? The file foo /a foo /b bar are what? Hard link, indicating that in the scanning of data blocks. So FSK know that, but inode link remain 1. Okay, so something wrong. So what a possible fix? What a possible fix in this case? Simply, how to fix it? Yeah, increase link count 2. Okay, because data blocks having a 2 hard link. So FSK find a hard link case in the scanning of data blocks, and inode say 1 link. So make it inode having hard link. Okay. All right. So that's the inconsistent link counts and lost of file. So sometimes there are some kind of dangling directories. So B, C, D, A, E, C, D, E, F. So you in memory system you create file G and persist it, and then you have to update B, right? Directory block, but G directory itself is persisted, but there's no directory block updated for B. Possible, right? Because G inode and G's data block is persisted, but this directory block is not persisted. So G has no dangle pointer. Then if file system find this case, then moving this one to lost and found. Okay, so dangling directory in the namespace, moving to lost and found. Okay, so that's it. So that is the basic operation. There are more complicated FSDK fixing scenarios, but these 4 are most popular and easy to understand. The other one, nope, I don't want to introduce. Much more complicated. Okay, so here's the examples. However, FSDK actually working through 5 phases. As I say, data bitmap, inode bitmap scanning, consistency between bitmap and inode, and name, the namespace scanning, etc. So that operation consists of 5 stages, which takes a long time. Okay, super long time. So FSDK with on 600 gigabyte takes what? 70 minutes. Okay, so a question. All valid unreachable files are moved under specific directory lost and found? Yes, true. Okay, so that was the consequence of the FSDK super slow. And also, it requires intricate, complex details of FSDK. So back in the days, early 90s, 80s, there was some kind of bunch of research papers to improving performance FSDK. So how to kind of delegate, how to make the FSCK performs better. Like kind of goes very details, kind of finding optimization for FSCK. Okay, fine, and not always obvious to fixing file system, and you don't know which one correct. So there are some kind of ambiguous cases. So then no. So some kinds of false positives possible, or there's some kind of ambiguous case that FSCK cannot fix it, and therefore FSCK is kind of partial solution, slow and not complete, but people can optimize it. Like FSCK works in some scenarios, right? So good. However, this is one interesting aspect of research. So systems, you are kind of optimizing FSCK when further and further. Then, nope, we have to kind of taking a completely different approach to solving crash consistency, which negates all the benefit of FSCK. The older kind of optimization research gone. And it used some cases, but most research is useless by new approach comes, which is called journaling. Okay, journaling is modern way. All file system integrate journaling. So as of 2023, I don't see file system which use FSCK. Journaling is the standard of providing crash consistency, which is called write-ahead logging. So write-ahead logging is a well-known technique in database. So file system guys borrows some database transaction concept, the transaction concept from database, and apply it to file system. So basic idea is that it record a log. So someone saying, so file system term is journal, which persist changes on disk data to separate location. Before applying the operation into your storage device, create some kind of specific location called log, and log and your on disk location. Logging first changes, and after changes applied, write back. So this also persist. So persist things, important things first. Transaction meaning batching. So important information like multiple blocks, directory updates, inode updates persist into log first, then apply to on disk location. This is called journaling. Okay. So write this update to their final location to on disk. On disk location, only after journal is safely written to disk. Only after the updates are safely persistent to journal. If crash happens, then discard journal if journal is not correctly updated, or redo updates because important things already updated, so you can reply. Okay, reapply journal. So when journal has to be multiple apply to this location several times, which is called idempotent, but let's not talk about in jargons. So if while updating this one, maybe this state is inconsistent, then reapply again. Okay, so journaling providing way to guarantee consistency. So require update, persist first, and then apply later. So apply can be multiple times. If crash in the middle, then you can apply again. So that is taken. Okay, and so on crash, your recovery operation compared to FSCK, recovery operation is just kind of applying the journal data to on disk location, so which is much faster than FSCK. Consequently, Linux file system, all the other file systems, or other file systems integrate this journaling operation. So let's zoom in the journaling operation. Okay, I think I crashed the Linux computer before I asked me to FSCK, or is it different? Okay, there are some kind of questions. Let me see. Journaling. When I crashed my Linux computer before it still asks me to run FSCK, or is it different command? Here's case. I think so journaling does not completely eliminate theoretically journaling completely eliminate FSCK use, but for performance reason in neural systems, it skips some corner cases. Okay, so in that corner cases, which really rarely happen, turn back to FSCK. So let's not talk about what's the corner cases. This is kind of consistency between block group descriptor and some inode blocks. So that's not really much happens. Journaling doesn't have it. Otherwise, you have to journal all the data, like superblock and the block group descriptor, which takes a long time to journal data. So just kind of an edge optimization, it skips it and then fall back to FSCK operation. So FSCK is much faster because it only focuses on that small cases. That's too much detail. Okay, does it make sense? So do we need to access 2 times every time single disk on write? Yes, but any kind of rational, generally your hard disk speed 2 times slow. Is it 2 times slower or not? There's some optimization. But why journaling still makes sense? Is this operation is synchronous, asynchronous? This journaling write-back operation. Synchronous? Do you want to implement this operation, which is called checkpoint operation? Checkpoint. So journaling. Is it synchronous? On fsync, you writing data or data to journal, the update journal, and also write back to on this location? No, asynchronous. So on fsync, writing, and this time is hidden in critical path, in critical performance path. So okay, make sense? Okay, it's clever, right? So it looks like a pretty simple idea. Okay, aggregate changes apply later. So what? But in the middle, look, if you zoom in this mechanism, it's beautiful. And again, this is kind of long debugged operation in database community, and file system guys actually kind of grab that idea. So it's kind of well made. Okay, all right. So let's take a look at the journal. So your operation is appending data blocks to data blocks. So data bitmap and inode and data block itself are updated, newly updated in memory. Okay, someone asked question, is the logging, why the logging is in memory? No, this is the journal. This is in disk. So file system formatter creates some kind of an initial part of your hard disk or SSD as a journal. So this update is first written to journal, which is in the SSD or hard disk. Okay. Right. So this information, DB, IN, and data blocks are logging into journal. So these two indicate these transactions. It has the heading blocks where transaction number 1. Okay, journal line. Okay, so finish journaling. Let's say, okay, and then you check a pointing. Is it correct? Is your journal implementation correct? There's some problem. What is it? There's a problem. So I say step 1. Okay. You have to ensure that journal is completed. Okay, so as a next step, you need the commit operation. Commit operation has to strictly ordered. So this operation, I and prime, the data bitmap prime, and data block done, right, and wait and write. If you skip the wait operation, what happened? What happened? Correct? So you just kind of, write block, write journal header and updates, and here, just write it. Is it okay? What's the problem? What are possible crash cases you have to take care? Think about it. Without waiting. So without waiting, maybe this block is not arrives. But journal commit block says journal is committed. So in crash, you may want data written to on disk location. Okay. So in journaling procedure, right. Within that, there's no waiting. So right PXB IN DB pointer data block. Then wait, which is called barrier. And write transaction. Without that, some blocks may not persist. Okay, but this journal data, journal record in the area says this transaction is committed. So wrong, maybe unarrived data, which may be garbage, can be applied to on this location. That's wrong. So you have to wait between these two writes. The file system providing way to making these two write having ordered. Okay. Then after that, right checkpoint operation is that this journal location journal data is applied to this on disk locations correctly. Okay. How long does it take? Until this two operation is finished. So synchronous write. So file system sometimes maybe make a request and return, but wait until this outstanding write operation is end. Okay, then if our file system confirms that all these blocks are written, then right, so that's kind of concept of waiting operation. It's not time. It's not about time. Event has to be finished. Check it. So make a request and poll. See that all this operation is finished or not. Then after that, write the data. This is implementation, but there's some kind of a way to make these two operations synchronous. Make operation having a barrier. It's important. If you miss it, your journal system crashes. You just said your journaling system has bug. Then right back. So for recovery, simple. The first case, maybe some blocks. Oh, one more question. Is it okay to reorder this blocks within journal. What happened? Does this happen when flushing or not happen only when page cache is changed? This operation happens when you call fsync. When file system call fsync and application fsync, then fsync operation involves this journal line operation. And this operation maybe is okay to come, switch it if there's a way to identify this is I know the block, this is data block, this is kind of a bitmap. If there's a way, then you can actually kind of it's okay to order. So after that, let's say this block is not committed. Journal is not committed and there's no commit block. Okay, so simply in this case, simply discard journal. So no update is applied. Okay, and then file system roll back to original state because on this location is remain untouched. So in this case, this update lost. You lose the update, but still lose update. But what? Okay, consistent. File system state still consistent. Recovery is. This case, no journaling block, no transaction block, fine, crash. Eliminate. So second case, when you are applying to on this location and journal is correctly committed, then redo. So overwrite final disk locations using journal metadata. So if you crash happens in the middle, then reapply data to on this location. Because all the information required here is updating the journal, so you can update data bitmap, inode data blocks multiple times. Okay. So these are two recovery. Discard or apply. Two cases. No intermittent. Journal is not committed, discard. Committed, multiple apply. Possible. Simple principle. Okay, that is the idea of journaling. Okay, any questions? There are some now I'm talking about some further optimization of journaling to improve performance, but that is the basic rationale, basic kind of design of journaling. Key things too, I mentioned that. Journal is on this area, and there's a kind of weight between journal data and journal commit data. And on this location is applied multiple times. Applying to multiple checkpoint operation, applied multiple times. Is there any cases where journal discard crash? Journal discard crash, what does it mean? Where journal discard crash? What do you mean? What do you mean journal discard crash? Journal is not discard where? No, because there's no transaction, the transaction commit blocks found. So in this case, always just kind of oops, sorry. So in this case, there's no discard case happening. How do you know whether it crashed between 2 and 3? Crashed after step 3. Okay, here's case. After these things are written, then journal is kind of file system say this is kind of finished. So apply. How can I say? So there is some kind of transaction 1. Each transaction looks like transaction 2. Maybe transactions are actually kind of logged here. Okay. After all transactions applied to the file system location and deleted. But it's not deleted, then file system know that this apply there is some kind of crash happens in the middle of applying the journal, and then do it again. Make sense?
then you have to work 3 times on this on write. I have to write 3 times. What do you mean 3 times, Jungtae? 3 times? Could you specify? 3 times. What? 1 times. 2 times. 3 times means yes. On the recovery, yes. But in case of recovery, your system is rebooting, right? So it's not affect application's performance. Journal is deleted after step 3. Yes. How they know crash happens while applying journal? Okay. After finishing the journal, there's some kind of some trick, like some put like a super block. So if journal has some kind of metadata block, this is implementation. So it's not design, general design. I just kind of explain one specific use case in the ext4. So it's not, how can I say, textbook like the example. But if you ask questions, I just kind of giving the example of ext4 cases. There are some kind of super block. So 0 means that it's now applied. After applying everything and right. After checkpointing everything, wait. Then update this journal. Okay, my journal, all data journal is applied, so you can reuse it. So update this block. Simply. All right. Okay. So yes, crash consistency. Okay, it's good. So crash consistency is kind of case analysis. So you can think about how can I implement correctly this case, this case, this case. It is good. So that's why file system remain the beauty of file system hidden is hide in the details, right? There are many detailed things. The file system is complicated things, but it's kind of interesting. So second thing, optimization. So you don't need to make the log space is limited, so you can reuse it after applying the journals, checkpointing journals. You can reuse it. So you reuse the log. So log is actually garbage collected using circular log, and this update is batching. So in the example, I just see the only one cases, but different thread may update this inode bitmap data block multiple times. Then you can actually kind of do multiple thing updates at the same time and commit it. So batch. You just batch updates. Okay. So before calling the AppSync, ext3, ext4 periodically make this operation, journaling operation every 5 seconds. Okay. One interesting optimization is checksum. So checksum is that you can actually kind of compute this 4 kilobyte blocks data and compute checksum and put into this journal block. Then you can eliminate what? Barrier between journal write and commit block. Why? Why do you think checksum can eliminate this optimization? So wait actually kind of barrier operation, wait barrier, write barrier, as I say, the write barrier between them is eliminated because checksum, just you can compare actually data blocks checksum and checksum data written in the transaction block. If they matched, then the file system knows that journal is correctly committed. Not matched, discard it. Okay, so using this checksum techniques, this barrier can be eliminated. But this is optimization. Important thing. Modern file systems. So for what do you mean? Inode data is just one block, right? But if you are update 1 gigabyte, and what do you mean? This data blocks should be 1 gigabyte. So your journal has to contain 1 gigabyte and copy 1 gigabyte. Can you see the problem? Okay. So, or journal size may be smaller than, let's say your file system updated 2 or 10 100 gigabytes updated. for some reason. But journal size is only 1 gigabyte. Then you cannot journal data. Okay, so because of that, modern file system eliminate data blocks out of journaling. So they only consider bitmap and inode. Consequently, what kind of operation has to be rely on the SIG? F6? What operation, for example? Because data blocks not journaled. So what operation using journaling? What operation we have to rely on F6? What operation? What operation? Link count. Link count requires journaling of this one. Right? So in some case, link count operation, you have to we have to run FSK to finding link count, for example, because this block is not journaled. Okay, so so that's kind of one example of we combine journaling and FSK, but let's not too much worry about this combination. Anyway, so you have to understand that this journaling mechanism is called metadata journaling, which is default, only guaranteeing the metadata consistency, not consistency between the directory block and inode. Okay, so which is called ordered mode. So if you look at the mount in Linux, mount -L, then you can see all ordered options. That means that you are only channeling metadata, not data. Okay, so this is first data right before journal is committed to any pass. Okay, so that's not the point, guys. So ordered mode, data written to on disk location first, then journaling inode and bitmap. Data to on disk location, then journal, journal, metadata. 1, 2, strictly ordered. So these are metadata journaling. So it avoids copying large data blocks. So this is one important optimization. Last thing. So this is last contents that I want to deliver for crash consistency. So we know that file system guarantee this optimization that only guaranteeing the consistency of data bitmap and inode, but not consistent with data block. But say in some cases you are to write, let's say this is page cache and this is disk. You want to update multiple blocks, right? So I want to update 7 blocks. I want to persist it, okay? But in the middle, it may crash. Again, in metadata journaling, I say the data is written to on disk. So here is an example. What you want to do is that I want to change in this block to update this block. And for simplicity, atomic unit, the basic update unit was 4 kilobytes, but for simplicity, for example, let's say just 1 byte. 1 byte is only atomically updated. So 1 byte is identical 4 kilobytes in hard disk, say. And you are using the metadata journaling already moving the ext4. Then what you want to do is foo bar. Okay. For applications, the perspective, what you expect is the foo and bar. Okay. So what's your choice? You may implement file system this. Open a file foo and write a file to bar. That's kind of common implementation, right? So I want to update this foo bar. Yeah, wrong? Yes, because what? Let's say I say that one block is atomically. So let's say this is 3 blocks and this one is 3 blocks. So if in foo, so you update B, A, R in memory, and you want to write back. If A is persist first, it was foo. A is persist first, then far possible. If R is persist first, then far 4 is possible. These are possible cases. However, in applications perspective, for recovering these cases, what you want to do is the only foo and bar. You want to atomically update this foo file state from foo to bar, and no intermediate possible case is not allowed for recovery. Otherwise, application programmers has to check all the cases and recover. That's bummer. So this atomic update, important requirements for applications crash consistency. I'm talking about application, not kernel. The kernel crash consistency guarantee by generally. Now moving to applications perspective, and I want to make this atomic update. This atomic update by journaling data. True? If I journal data, like previous original journaling, data journaling code, then we can achieve atomic update. True? We mean that programmers can use atomic update. So file states can be either foo or bar, true or false. Are you guys following what I'm talking about? Okay. Okay, let me introduce and let me explain again. So when I looking at some kind of program, many web programs and other programs, I see many applications don't understand the file system semantics and do really kind of buggy implementation of crash consistency. So that violates atomic update. Atomic update, I'm saying file state should be full or the state updated. And then for this example, let's say 1 byte is atomically updated. So you can actually think about this case is kind of 3 blocks, this case is 3 blocks. So foo bar A. So in-memory states are changed by foo to bar and persisted. And this is 1 blocks each block. If this block is updated first, then file. If this block is updated first, then crash and file. So these are intermediate states. I don't want to. What I want to is in a foo or bar. Otherwise, you have to take care of all the cases. So this atomic update guarantee is important for application crash consistency. Then my question is, if you are using the original journaling, which journaling the data, is it this fast the operating system guarantee atomic updates or not? That's the question. True or false? Okay. If file system guarantee this file system journal guarantee journaling data, all the data journal is this data update are journaled and checkpointed. Therefore, okay. However, due to this optimization, metadata journaling, I say that I use metadata journaling. This atomic update is not applied because when executing this operation crash, there are possible inconsistent states exist in your storage. Okay, so who is having but atomic update is important in a future for recovery, and file system does not guarantee atomic updates. And who has to enforce protocols for atomic update? Who should do that? Who? Kernel give up, right? Who? application developer, you, okay? PHP programmer, JavaScript programmer, okay? And any kind of the database programmer, web front programmer has guarantees of time update. Let me give you an example. This is really important, so I want to let you know. So you see that this kind of board, right? In the board, okay, you are attach figure. This figure has, say, 1 megabyte. So when you're as an application developer, you just write figure. Done. That's what you do, right? So the post text written and figure, right? Post in your system, and then write figure. Okay, this is common implementation, right? But if you are crash in the middle of writing a figure, this is your figures, for example, figure A, B, C, the multiple blocks. Some blocks not applied, so the figure is broken. You can see kind of some broken figures because this figure has multiple blocks, but file system does not guarantee atomic update. So you can see some blocks applied, some blocks not applied, but stored. That's possible. Okay. So to avoid this one, application developer has to build their own protocol for atomic updates. Okay, question. How to do that? How to apply the atomic updates? How to do that? Lock? No. See, what kind of an idea you can learn from the file system? Atomic updates. What idea you learn? Journaling in web, in system level, user level. System level, user level. Journaling in user level, system level, user level. Okay, so you, application developer, has to write their own protocol for journaling. So I say this is rollback logging. There are two types of logging: write ahead logging, write rollback logging. Rollback logging. So there's the original file. You can copy original file into log. After that, update it. Crash happens, you can actually kind of report it. Possible, right? Okay. Okay. So, or new update comes to new file, and then apply it. This is rollback. This is write ahead. Okay. So here I create a log. So what's the possible? This is example of journal, right? New update comes to log, and on original file apply later. Copy original file log, and new update comes to original location. This is rollback, and this is write ahead. So journaling is the case of this write ahead. I just implement rollback style logging. So I create log and copy data. So what I want to do is food to bar. So copy data as an application developer, and write data to the file, and delete the file. Correct? So this one is kind of non-crash content, kind of who programmers written by who doesn't not know about file system at all. So someone who knows file system having this crash problem, so then create a rollback logging this way. Correct? Bug or correct? Buggy or correct? Correct. Correct? Do you think correct? So the thing is, these two operations can be changed because in memory system, log file and this file, the write data to file, write data to update data to bar can be reordered. So this operation happens first, then crash. reorder, crash. Then same thing. Your original file crashes. Okay, incorrect. So this is file, right? File's possible cases, wrong. So what do you have to do? What's the problem with this implementation? What was the problem with this implementation? Reorder, right? So how to prevent reorder? fsync. Okay, so create the file and copying data, original contents of file data food to log and fsync. So wait until it's persisted first, then write the data and fsync and delete the. So these are clearly kind of prevent reordering. Why the second fsync required? Why the second fsync required? If you miss fsync, what happened? Let's say if our system, this system called reorder. What's the problem? What's the problem? If you miss it, what happened? Unlink happened. So unlink and write happen, then crash. Then you go to this scenario. Because log data is deleted and you update the original file. Then this same scenario like this. So you have to prevent unlink before persisting data to the file and delete it. After all the updates done, waiting unlink file. Okay, I'll get back to your question soon about that. So, thing, correct? No. Still wrong. So if you are reaching to this level, I think you are a good programmer. You have some kind of knowledge about fsync information and why rollback logging style for crash consistency, application crash consistency. So look at this code. Okay, you are kind of kind of upper middle level programmer, but still something missing. What is it? This is hard. For understanding this, you need a kind of OS level detailed knowledge. What a possible problem. Thing is that directory A may not contain directory block. May not updating. So like lost and found case, /A has no contents for log, but log file exists. It's possible, right? You can see the previous inconsistent state. So a false or the application cannot locate log, cannot recover the contents. So incorrect. So how to avoid this scenario? What do you have to do? fsync A. Okay. Then correct. So to update foo to bar as a crash consistent update, you have to follow this protocol. Create a log and copying original contents, fsync, then fsync directory. This fsync can be is it okay to place here? I'm not sure. No, you should not. So this one. And you have to follow this protocol to correctly update food to bar atomic update protocol. So what do you mean? So you have to understanding authenticity, ordering, and durability, including directory blocks. That's the application level crash consistency. Again, for that part, you have to file system kernel file system design. Because ordered mode providing metadata only journaling, atomic updates, you have to implement this way. That's correct way. Again, the idea of this crash consistency is also kind of we learn the kernel journaling. So we learn journaling and then using this protocol for crash consistency. So after taking the course, as a developer, please, in the case of your crash consistent updates are important, please understand this protocol. Okay. So I see a lot of bugs in kind of random GitHub implementation who don't know about file system at all. See that. Why can't West do this atomically? Again, data journaling. To do that, you have to do data journaling. Data journaling, what's the problem? If data is 100 gigabyte, operating system handled all the cases, right? If data is only if data blocks only kind of few megabyte, yes, then by default, operating system can support data journaling. But OS can consider all the possible corner cases in case the data is 100 gigabytes, so give up. You can do it by giving option O data score journal. Then the atomic update guarantee is by operating system, but by default, operating ext4 ordered, which only guarantee the consistency between these two. Does it make sense? Okay, so here, kind of intricate knowledge of journaling, and that's consequence of operating system delegate this responsibility to application for that reason. Okay, will it possible to automate these steps? No. So interesting, right? So this is kind of pretty complicated corner cases. No. So there are many kind of tools to finding these bugs. So some kind of model checking tools to identify these crash bugs. There are lots of research there to finding bugs, but there's no automatically code generation for that. I don't know. Maybe Copilot understand this one to generate code. I don't know. I didn't use it for that, but I didn't. As far as I know, I don't know. It seems too exhausting for just writing a data store. Why kernel just not providing API for atomic updates? No, because atomic update journaling is not just kind of changing the mode switch. When you are formatting the file system, you have to either order the mode or data journaling. There's no kind of mixture of that because its implementation is complicated. Okay, so again, I just giving the example of this application delegation of crash consistency for atomic updates because kernel only guarantee order journaling. All right, so that was the interesting example of understanding why kind of application developers need to understand the kernel, and I think we are almost there. And then let me kind of explain the last slide. All right, so we're there. Okay. There's operating system. Oh, before that, maybe I can. This is just kind of conclusion slide, so I didn't post it, but it's fine. You just feel free to see. Someone actually asked the question. The synchronization problem. Order violation. So let's say this is thread T created. So T is allocated, and T you can refer T some state access. So the order allocate first and use later is strictly enforced. If this thing happens first, then what's the problem? Then what is the problem? Okay, I just kind of quickly switching the context. Maybe you guys confused, but someone asked a question why this one is not prevented by lock. So I just can ask you if this 2 happens 1, 2, 1, 2 is correct order, but two happens first, one happens later. What's the problem? Key is not initialized. Access. So use before allocation causing segmentation fault. So this order always has to be enforced. So maybe you know that how to you know the lock primitives. Lock one, unlock, lock, unlock. Is this lock implementation enforce this ordering? So if you put the lock between them, does it solve the problem? No. Why? Two cores execute this one first. So they are executed atomically, but this one executed first, executed later. So problem. So lock never solve this ordering enforce. Lock only solves atomic operation. Lock only guarantee that the critical section between locks are executed atomically, but ordering with the critical section between two are not enforced. So what is the primitives to enforce ordering between two different critical sections? Conditional variable. Handbar is only way to solve this one. So you have to put the conditional variable to say that after that, signal executed. So that's it. Does it make sense? Number two case. What do you mean number two case? Number two case. Number two case. I'm talking about thread. Thread to access state. So in this case, before let's say this is two thread. Thread one, thread two are executing two different core. But this thread are executed before this allocating this thread. Then you are this T is before allocating, so it causes segmentation fault. So allocation always happens first, and then use it later. The strict ordering. Is it possible to execute thread to before made with? Yes. Let's say this is function one, this is function two. Then possible, right? So implement two different functions. One function initialization, two function use it, and for some reason you can actually kind of make this on two different threads and crash. This is pretty common pattern in many complicated systems, actually. Yes, a lot. There are a lot of examples for this one. Okay, so that's it. That's the thing I want to explain. All right. Okay. So let me kind of conclude this lecture. Okay. So back in the first class, do you recall this problem? So I asked then, what's the problem? Okay, I execute two times, but nmap speed changed two times. Yeah, why? Why this nmap left set takes like 10 times difference? What was the reason? We remember that? Cache. Okay, so I want to make the data set 1 gigabyte, then still having 2x. Why? Now you can easily get it, right? You learn concept of what? Demand. Okay, so now we can associate this operation, what happens underneath in the kernel, and you can guess it. Okay, so if you can easily understand this behavior, I'm successful for this course. So you know that. Okay, because kernel do demand paging. I know what's demand paging. Virtual address, physical address, kind of separated for abstraction. Virtual address when application access, page fault happens or located later. So first time, page fault keep happens for the first access. Second time, page table mapping. So no page fault happens. So no, to watch faster. Why? Because this design code is the page. End of story. Yes, good. Okay. Again, that was the purpose of I teach operating system. You need to know concept of operating system practically. Second, the last slide. At that time, you saw this picture. You may not understand, I guess, but as time goes by up to this end, like we learn the designs of operating system. I said this design thinking, implementation. Design thinking I'm talking about for protection, set the goal, and there's some kind of goal of protection, what API to design, what kind of efficient mechanism I can think about with design. Then going to implementation. There are possible implementation strategies. So one possible question is like, what kind of hardware protection I use? What kind of hardware mechanism to use it for protection? Okay, so rings privileges in CPU, or ARM having different privileges, but all this implementation pointing to kind of design concept of protection. Okay, and then what part of is done should be done in hardware? What part of done is software? You have to kind of distinguish, right? And how to separate software layers according to protection. These are kind of implementation. And goal is kind of protection. So we can have there some kind of blurred area between design and implementation, but in general, you can think about high-level goal and implementation separately. So first, you can think about design and then do implementation, and you have some knowledge about, and you can actually kind of fixing. You can kind of reevaluate design and then go back to design again and implement again. So this cycle. Do you understand what I'm talking about? I just kind of, giving the example throughout this course. Do you understand what I'm talking about now? Can you guess? Design thinking, implementation, high-level goals, implemented. When you start implement, you know that, oh, I need to fix these design goals. And, fix design goals and implement again. That is cycle, typical cycle of operating system. And that is how you need to understand operating system. Please, if you can understand this picture, I'm happy to that. Okay, I just kind of successfully delivered important contents for you. This is kind of high-level message I want to deliver. All right, so these are key rules of operating system. We learned several designs, abstractions. So what abstraction? Process, virtual memory, files, etc. And we define APIs and how for applications use. That's the first goal. Second is protection and isolation. So how contain applications behavior and how protect operating system from malicious or buggy application. How to isolate one application another. When application goes infinite loop, what happened? Protection. And then sharing. For sharing, you can see two different time shared, space shared. Time shared, scheduler, space shared, memory reclamation. So these are three important goals of operating systems key role. Then, in the future, maybe you may encounter virtualization. Virtualization is like, kernel mode, user mode, operating system is going to upper level. And then you introduce a new layer called hypervisor. And then here. So these are virtualization design. By looking at this figure, what kind of thing you can remember? What kind of design requirement you can get from the past of operating system? So OS providing protection for each, providing use abstraction to use hardware and sharing protection and isolation application. So hypervisor, same thing, providing API and abstraction for operating system, because operating system is treated as a process in the view of hypervisor, providing new abstraction. So we are using the different mechanisms, but design principles are similar. Sharing, yes, process sharing, hypervisor providing sharing between operating system. Protection, yes, how to enforce protection between guest operating system using page table. How to isolate the application or to create, confine the behavior of malicious guest operating system. That's hypervisor. By looking at this kind of similar structure, system structure share same design principles across different, even if they are kind of completely different, underneath the design, they share. So in the hypervisor, in virtualization, we learn some different techniques, but design principles are identical. So beware of that. Okay. All right, so that's all for this time, and I think this is kind of end of this last this is last class of this semester. And thanks for you kind of following this complicated lecture and all of the long lectures. And I'm happy to giving this lecture this time. And hope you good luck with your kind of the remaining stuff, Pinterest quiz and then final exam. Okay, so thank you, and let's see you next Monday in the exam class. Okay, thank you. Now, take care, guys. Exam time and the location will be posted in the Piazza soon. Take care, guys. See you in the class. See you in the exam room.